Thumbs up. All right. Hi, I'm Mark Allen. Thanks for having me. I'm going to talk about Erlang and Go concurrency tonight. I'm also the coordinator or facilitator for the Houston Functional Programming Meetup that meets usually the night previous. We have a lovely venue, but it's not as lovely as this area. But thank you to our lovely sponsor. They are a company that is called Bridgeway, and now they're called something else. Don't watch this. Okay, so I'm going to talk about how Go concurrency and Erlang concurrency are similar and how they're different to each other. And what I really wanted to do tonight was just really explore kind of the concepts underlying a lot of the concurrency models, because Erlang and Go share some similarities in the way that concurrency works, and they also have a lot of differences. And one of the reasons that they have differences is because of the semantics and the formalisms in the papers that were influential in creating those concurrency systems. And so I just want to explore a little bit about that tonight. I also have a cameo by Edsger Dijkstra, who you really can't talk about concurrency without talking about Dijkstra at some level. So we're going to have a little bit of talk about Dijkstra, and then I'm just going to kind of go into the main differences, and then I have sort of a live demo or some code that I wanted to run through and show you guys how things are similar and how they're different, how the Erlang code reacts in certain situations that are different from Go code, and how Go code has certain assumptions built into it that Erlang code doesn't share. So we're just generally going to explore these concepts tonight. So I hope I see now that my fonts are a little too small, But yeah, so here's my name. It's really tiny. Sorry, but it's Mark Allen. I work at Basho. Basho makes fine databases for your amusement and use. I'm at biteme.org on Twitter if you want to follow me there, and then my email address is down here if you want to send me an email or whatever. That would be great. Also, later on in the slides, I have a bunch of URLs that point to GitHub repo for this particular talk, all the code samples, the slide deck, blah, blah, blah. And then I have 6 other resources that I'll briefly run through, and then hopefully there'll be some time for questions and we can discuss this a little further. So the first paper I wanted to talk about tonight was this one. It was written by a guy named Carl Hewitt. There's a picture of him. Carl Hewitt worked at MIT for a super long time. He's at Stanford. Now he's a professor emeritus, so he's mostly retired, but he still shows up from time to time at conferences and stuff. I actually got to meet him in person last year at Erlang Factory, which was pretty cool. Anyway, in 1973, he wrote this paper called A Universal Modular Actor Formalism for Artificial Intelligence. And you can see it's up here. Sorry, but the font's really small. And this is actually an OCR scan of a typewritten paper, so it's actually not that great of an OCR scan, too. But what this paper does is it outlines a lot of nice properties for independent actors. And the independent actors are the unit of concurrency in Erlang. And this paper was very influential when Erlang was being built in the model for which they wanted to use concurrency. There's a great article that I have a link to later on that also compares Go and Erlang's concurrency models. And the author of that talked about how Simula was the first programming language that actually implemented actors, not to this specification, not using the symbolism and the semantics of this paper, but it did support sort of an actor-style concurrency model, if you will. And the other thing that was really interesting to me as a language historian, and if you go on YouTube and you type in Mark Allen and Strangeloop, I have a talk from 2014 where I talked about the early history of programming languages. Smalltalk was actually a language that included actors for message passing. And if you may know, Smalltalk was sort of the progenitor of object orientation as a programming discipline. And the method of passing messages back and forth between objects is very Erlang-ish. If you read the papers that Smalltalk generated, you'll see that a lot of the formalisms kind of drive towards Erlang semantics, which is really interesting to me. Anyway, in the model, you have a set of actors. They're completely independent. They don't share any memory. They don't share any communication. They don't share any variables or anything like that at all. And they're independently acting. And the only way that they can communicate or share data with each other is by passing messages. And the messages in Erlang, anyway, are untyped. So there's no explicit typing of them. It's up to the programmer to be able to tag them appropriately, send them across to the right place, deal with them in the right place, and all those sorts of things. We'll get into some of that a little bit later on as I get into code examples and things like that, but that's the gist of it. This is a really interesting paper. I don't really know what to say about it exactly. It's a little bit like reading Moby Dick, if you will. Moby Dick was this very long novel written by Herman Melville. It's a wonderful novel if you've never read it before, but it's very discursive. So it goes into a lot of things that sort of don't seem very that don't drive the narration forward. And this paper is a lot like that in some ways. It sort of discourses into a lot of aphorisms and things like that. Anyway, it's an interesting read. So dig it up. You should check it out. It's very it's entertaining and definitely not dry like a typical academic paper. The next paper I wanted to talk about was this one. I'll step aside here so the screen's better. The picture of that guy is that's CAR Tony Hoare, who's still alive. He is a very famous computer scientist. Carl Hewitt is also a very famous computer scientist. But Tony Hoare is even more of a famous computer scientist, as fame goes for computer scientists, I guess. He won the Turing Award in 1980. Turing Award is sort of like the Nobel Prize of computer science, if you will. And he's also been all over the place, all sorts of interesting disciplines. One of the things that was very interesting to me was that he was a contemporary of Dijkstra's. He actually learned ALGOL from Dijkstra and this guy in England named Peter Landon. Peter Landon wrote another paper called The Next 700 Programming Languages, which is a very interesting paper in and of itself. If you want to learn more about that, I have a talk that I gave at Recon last November, which is also on YouTube, and I have a link to it later on. And I talk about what the next 700 programming languages are, and Dijkstra's history with concurrency, and a whole bunch of other interesting stuff. Anyway, he wrote this paper. This was published in 1978 in the Communications of the ACM, and it's called Communicating Sequential Processes. This is a fantastic paper. It's a wonderful paper. Strongly recommend that you should read it at some point in your life. It's really great. What it does is it succinctly describes a method for independent concurrency units that he calls processes in this paper to communicate with one another by exchanging messages. And what happens is that the messages come into a certain part of the code, and there's guards there. And these guards are essentially conditions that have to be met in order for the guard code underneath it to be executed. And in this paper, he describes probably about 25 different computer programs, computing problems, specifically about concurrency control, deadlock control, multi-programming, divide and conquer, like work strategies, all sorts of very, very interesting problems that can easily be solved concurrently or in parallel. And he describes a way to do that with using this communicating sequentials processes idea. This paper extends an idea that Dijkstra developed. So I'm going to pull up the next slide. This is a picture of Edgar Dijkstra, who is sadly no longer with us. Dijkstra worked at the University of Texas for a long time, and before that he worked at Burroughs for a super long time, and he has sort of single-handedly grappled with concurrency control and multi-programming and distributed systems and all these things for basically his entire computing career. He's also a very prolific paper writer and has written a lot of very important seminal papers in computer science. He's probably best known for his graph traversal algorithm, so you probably know this one. It's basically calculating a weighted graph and then traversing the graph with the least weight, so you make a cycle with the least amount of effort. He invented that algorithm and published it. He also wrote a paper, actually it was a letter to the editor in the Communications of the ACM called Go-To Considered Harmful, which a lot of people have heard of. Dijkstra was a strong advocate for structured programming as a discipline, and the reason he was an advocate for that was because concurrency control was, in his day, and remains now, a very hard problem to solve. It's a pervasively hard problem to solve. And one of the reasons we're here tonight is because we're going to explore some of the ways that Go and Erlang provide facilities for programmers to reason about concurrency in ways that are easier than just sort of, certainly in Dijkstra's day, when you had to do multi-programming, what you were actually doing was writing machine code. So there was no help for you. You had to write every single thing yourself. And not only that, you had to write it in machine code. So it was really, really hard, right? When Dijkstra was writing multi-programming operating systems in 1968, there wasn't Unix, there wasn't C, there wasn't things that we think about as systems language programming. What they had was machine language. So that's what they were writing their code in, and that's the kind of concurrency control that Dijkstra grappled with early in his career, and then later, after more of these aids came into wide usage, he advocated doing structured programming as a way for programmers to reason about concurrency, in a way that was systematic and formalized, rather than just sort of haphazardly slinging code together and hoping for the best. We all know that that doesn't necessarily work out so great for everyone, to put it charitably. So Dijkstra is a towering figure in distributed computing, specifically in concurrency control. And since we're talking about concurrency tonight, I thought it would be a good thing to talk about him a little bit. Also, I'm contractually obligated to talk about Dijkstra because I think he's personally a very fascinating person. There's also no biography of Dijkstra, which is sad because there deserves to be one. He's a very, very interesting person and has written, as I said, a lot of really interesting work in his life. Anyway, I want to move on to just a slide that sort of gives you an overview of Erlang, the language, some of its semantics, and some of the concurrency things that it provides. First of all, there's a little bit of terminology that I wanted to go over. So Erlang has this concurrency entity that they call a process. The process is not like an operating system process. It's a process in the context of the Erlang runtime system. So it's very lightweight. It takes about less than 1K of stack space to allocate a process, and it takes just a few microseconds to actually allocate it within the runtime system. And the processes are also reaped and garbage collected on a per process basis. So Erlang, unlike Java or unlike some of these other shared memory systems, doesn't have the sort of stop the world garbage collection system. When a process dies, that's when the Erlang runtime system collects all the garbage, all the memory that's been allocated to a process back into the heap that it allocates memory to all processes from. The processes, when they're created, get a specific identifier that's specific to a node. One of the really neat things about Erlang is that it has that for free, quote unquote, and remember these are scare quotes, so you should be scared. It provides a way for you to do distributed processing. So in an Erlang runtime system, you can have an Erlang node on system A and an Erlang node on system B, and as long as you set up the system with cookies correctly, so Erlang has this really primitive access control system called cookies. As long as you set them the same, it has a daemon called EPMD that actually will do the RPC for you. So it will be able to exchange messages from a PID that's running over here on node A just as easily as it would over on node B. To you, the programmer, it's location transparency. So you don't really have to care about where a PID is instantiated at, but you do have to direct it to the PID. So you have to know you have to know the identity that you want to send a message to, but you don't have to care about if it's running over here or if it's running over there, if it's running over on some system that's 1,000 miles away or whatever. I'll skip over that bullet point. The messages in Erlang are not typed. So Erlang is not a strongly typed language. It does have types. Don't get the idea that it doesn't have types, but they're not enforced. They're not enforced by the compiler, at least. They're enforced at runtime. So I guess the sort of academic way to put it is that it's weakly dynamically typed. So it does have types, and we'll see that in some of the code that I'm going to show you later on. But the messages that you pass are completely typeless. They only have meaning intrinsically to whatever you give them as a programmer. So you can send a set of integers to a PID or whatever, but if that PID doesn't know how to deal with integers, then those messages are just going to sit in its mailbox for a long time. So the other thing I want to talk about that's sort of really important to know is that Erlang variables are immutable. So once you set a variable in Erlang, you can't set it again. That will give you a runtime error. The compiler will actually complain about that too. Or at least it will definitely give you results that you didn't expect. So if you try to assign a value to a variable name that you've already used before, Erlang will complain and will not compile its source code. Question? No? Processes share no memory. They share no data of any kind. There's no way to share data across processes at all. The only way you can communicate or share data is by using messages. There is an asterisk by that. That Erlang contains a very nifty caching system called ETS. That's Erlang Term Storage. That is an off-process way to share things between systems without sending messages back and forth. But that's an asterisk, and I don't want to get into it tonight because it's too complicated for this talk purpose, unfortunately. If you are interested in ETS, talk to me after the talk. I would love to talk to you about it. It's very neat. Anyway, the other semantic thing I wanted to say was that Erlang's approach to error handling is very different from Go's. So in Go, typically you'll execute something, you'll check for an error value. If you get an error value, then you'll handle it somehow, right? And that usually happens at the call site immediately after you do the call. What happens in Erlang is typically you just write the code as you want it to go, and if you get some sort of exception, the Erlang process dies. So the typical Erlang response to errors is for that process to completely cease to exist. And there's a top-level supervisor that spawns all these workers, all of these processes, and it notices and says, oh, look, that PID died. I'm going to start it up again, and it will get a clean new state. Now, whatever state it had will be lost, right? But it will start up a new worker, and it will take the place of the one that died. So there's that. Are there any questions about any of this stuff so far? Yeah, Chris. They can, but they don't inherently have state, right? So you can have as much state or as little state in them as you wish. Does that answer your question, or are you driving at something else that I'm not picking up on?
No, I'm just you're saying that the variables are immutable.
Yeah.
So how would a process manage? How would it have state?
That's a really interesting question. So I'm going to get into that a little bit later on when I go through the code examples. But for right now, what we can do is that the thing that's not on this bullet list and that's also important to know about Erlang is that the only loop construct in Erlang is recursion. Okay, so there are no for loops, there are no while loops, there are no anything like that. It's all recursive calls. Erlang is tail call optimized, so it's efficient at doing recursive calls. But the thing is that so the answer to your question, Chris, is that when you go through an entire section of code and you want to call it again, you put the modified state in the new call, and then that state gets changed at the top level of your function. So as you go into the function, the recursive call will have the new state entered into it. It sits within the process memory itself. So all the memory is completely allocated on a per process basis, and it's collected on a per process basis.
Oh, okay. That answered my question, which was if you have A and you wanted to add 7 to it, and you wanted to reassign that to A, you can't do that.
Can't do that.
But only in the context of the process.
If you're doing a procedure where you needed to take an integer and add a number to it and then store that temporarily, what you would do is you just use a new variable name. And so it's a very common idiom in Erlang to have like let's say that you have a number x and you want to add 7 to it, then you would just have x1 equals x plus 7, right? And then you would use x1 as the result of that and carry that through your code. So that's a very common Erlang idiom. You're going to see it in the demo code that I'm going to show you in a little bit. Question in the back?
Yeah, what happens when the supervisor dies?
When the supervisor dies, there's actually a top-level supervisor called a group leader. The group leader is responsible for restarting those supervisors. So it's supervisors all the way down. Yeah, a question in the way back.
Gigantic recursion.
So Erlang processes are not threads, but they are lightweight?
They are super lightweight. They are not green threads. They are not coroutines. They are not p threads. They are not whatever. They are specific to the Erlang runtime system.
Okay, and also they can only communicate through messages, so the sanctity of their state, whatever state they have, it's not protected by the operating system, it's protected by the runtime, or what?
Do you mean in terms of memory corruption, or?
Right. How does the OS or the runtime ensure that the message passing mechanism is the only mechanism?
Because of the way that Erlang lays out memory and allocates memory for processes, the runtime provides a guarantee that your memory is not shared with any other processes that are running or will be run. and it's not garbage collected until that process is dead. There's an asterisk there. The asterisk is about very large binaries. Okay, so Erlang has an optimization that, let's say that you have a 64K JPEG sitting in memory, right? You don't want to pass a 64K JPEG around to 1,000 processes. So what Erlang does as an optimization is it passes a reference to that, but it treats the data as immutable. So once the data has been assigned, that doesn't protect you from like random solar flares or like bizarre disk drive head crashes and whatever failure scenario you can think of. But as far as the Erlang runtime system is concerned, once the data is in memory, that's it. It's not ever touched again for writes. You can read it as much as you want, and that's what they do. That's what the shared binary thing does, is it lets you read it multiple times with a reference, but it won't let you write it anymore. You can't write over it. You can't write to it. You can't even rewrite little parts of it. So
Until the process dies, right?
Till the process dies. Now large binaries are reference counted, right? So if you share the reference across 5 PIDs, let's say, then that's not going to be garbage collected until all 5 of those PIDs are dead. And what we found, especially at Basho, is when we have very large memory, very large binaries in memory, that actually is a problem, which is if you have a very long running process and it has a reference to a chunk of memory that's very large, you can have memory exhaustion problems. And that does come up from time to time, unfortunately. But generally speaking, I think this is a really nice way to handle memory and garbage collection.
But for those big binaries you have a problem with, does the OS have any leeway to swap those out to disk? Manage it for you?
It has the normal interactions with the Erlang runtime system. So the Erlang runtime system itself has its own scheduler. It manages allocating what it calls reductions to processes and functions that need to be executed. And so it will, by default, assign, it has 2 schedulers per core. So like I have a 4-core laptop here, so there's usually 8 schedulers that are running. And then it'll run 2,000 reductions, and then it will swap off that and then put on a new function for execution.
It's still at the mercy of the operating systems.
Correct.
Management, page management, the whole nine.
Erlang does not handle those things for you directly. Yeah, so you still have to deal with the operating system layer at some level. But in terms of scheduling its own internal work, the processes are lighter, the processes are lighter, and the scheduler is more efficient at detecting when work needs to be moved off and when work needs to be moved on. So, any more questions before I move on? No? Okay. All right. So I have a much smaller bullet list for Go. So the Go concurrent entities, I'm sure you all know, are called Go routines. The messages, I like to think of them as events, are sent on typed channels. Go is very strongly typed, unless you use an interface type, and then they're not as strongly typed. The processes share memory. I know that Go has gotten a lot better at garbage collection, but there's still long garbage collection pauses where long is defined as, a second or something. Not as bad as Java, but still long in terms of the distributed system timeout. And it has mutable variables, which is more in line with what most people expect from a programming language. I know that when I first started learning Erlang, just as a personal aside, I went through this trough of depression where I hated everything about it, and then as I got more facile with the language, I felt like, oh yeah, I get it now. Like my brain turned a corner, and I was like, okay, this makes sense to me now. So it's good stuff.
Is Erlang opposite Java?
I don't know what that means, but probably.
Culturally, yeah.
I would say in most ways it probably is. Erlang is a very niche little language. It's a wonderful language. It lets you do a lot of really cool distributed systems work. But it's a small community, and the people who created it originally are active within the community. They're also very accessible and very nice people. You can fire up emails to them, and they will answer you, and not be stuck up sticky birds about it. They're just great folks. Question?
As an aside, I know that if you didn't know, the Go 1.6 release improved the garbage collection guarantee. I believe they're now at 10 and 20 millisecond pauses.
That's awesome.
Yeah.
I know that's been a huge area of focus within the team, and I have been following it kind of at arm's length. before I joined Basho, I was I wouldn't say I'm a super strong Golang programmer, but I was pretty active in the Docker project for a while, and I was doing a lot of pull requests for Docker, so I was using Go quite frequently, and so I was more involved with the Go community at that time. But now I'm more of a Go hobbyist at best. So yeah. And by the way, if I make technical mistakes tonight about Go, feel free to offer up corrections or what we need to fix. Totally open to that. So I wanted to kind of go through some code examples that I have, and these won't take too long. It's a super simple problem. I read this really fascinating blog post that talked. Can everyone see that? Is it big enough, or is it even visible?
You have a nice background.
We'll find out.
Oh, there it is.
Ooh, too big.
What?
Oh, that's definitely
It's
too
larger
big.
than your screen.
Oh,
Definitely.
that's not good. Oh, there's my cursor. Let's see here. Oh, it's at the bottom.
Yay!
Hey, look at that.
Good? Yeah? Okay.
Vim times data.
Okay, so I have this really simple little package here. I should have turned on display mirroring, but I'll just do the best I can. And what this does is it does a really simple computation that calculates a times table, and it calculates all of the quotients. All of the products from 1 to 12. So it's 1 times 1 all the way up to 12 times 12. And it does this concurrently. It does it across 12 different Go routines. And that's basically what we're setting up here. We're setting up some wait groups, and then we're calling our Go routine times table n, and then we're basically calling wait. So we're going to do some work. Now, I will say that as an Erlang programmer, it was really surprising to me the semantics of how concurrency worked in Go, which is to say that if you don't put wait groups in and stuff like that, then Go will not actually do anything at all. It will run through your code, and it will skip over the Go routine, and it will just end. And you'll be like, wait, what's going on here? Yeah, Ryan.
Is a wait group is for like a future then?
It's more like a what I would call a mutex. It's more of a semaphore. Does that make sense?
Well, okay, yeah.
It's basically a way to count how much work we've done and how much work we expect to get done.
Do anything if you don't, yeah, okay.
Well, I mean, it technically does something, but it says, well, I don't have to wait for the results of this, so I'm just going to execute and finish. Yeah, so the Go routine technically gets created, but it actually doesn't do any work. And then the program ends. So eventually I figured that out. I'm not that bright, but I did figure it out eventually. Yeah, so what we have to do here is we create a wait group inside of this for loop, and then we call a times table, which is just a nice little function down here. And you can see that this is a real simple one. We just basically have a counter from 1 to 12, and then we just print out some stuff on the screen. There was originally a sleep in this particular code example, and then we call wait group done down here at the very bottom. I know it's hard to see, I'm sorry, but there's a wait group done at the bottom, and then that actually, as wait group done, it gets executed, it decrements, which is almost exactly how Dijkstra describes semaphores. And so when that goes to 0, then the wait group wait terminates and the whole program finishes. So what I wanted to do was to actually show you what that looks like.
Mark,
Yeah.
I take it there's a function hoisting in Go. Since times table is defined below where it's being used.
Yeah.
Is that right?
Yeah. Yeah, the Go compiler is smart enough to figure out that it has a definition that follows behind the main program. And also a really common Go idiom for concurrency anyway is to have an anonymous fun that is your Go routine that sits there and executes. So a lot of times people inline the concurrent function. Oh, I typed Go wrong. That's funny.
G1.
All right, so we're pair programming, extreme pair programming. Yeah, so if I typo things, you guys need to tell me, okay? All right. So I'm just going to times this just to see how long it takes. Sort of the interesting thing I wanted to point out here was that it's totally random what the sort of technical fancy word for this is non-deterministic. What order we get the results back from these Go routines. In this particular case, it looks like the 5 sequence was the one that was last. If I run this again, it's likely going to be some other number. But you can see here at the bottom that it took 0.765 seconds for the Go system to compile the code and execute it and output the stuff on the screen. Just for fun, I'm going to run it again. And this time you can see this time the 11s were the last one for whatever reason. 5 was second to last. And it will just keep doing this over and over and over again. So I walked through the Go code. Really simple. If any questions about it, it's really straightforward.
What is the Go? What is, when you have the keyword Go, what?
That basically says here's a block of code that I want you to spawn into a lightweight process.
And then if there's an into it, which is that wait call, or?
Yeah, so the wait group, what it does essentially is it says, okay, we're going to execute.
Can you reopen? Sorry, can you reopen?
Yeah.
You did a very good job with
Thank you.
Also, why did the time decrease by 2/3?
Probably because the cache was hot and it didn't have to recompile anything.
That
It's like a bytecode type thing.
Like on, okay, so
No,
like
it's
line
not about Go,
14,
but it-
like line 14, you're calling.
For example, disk hash.
Yeah, right here.
And are you passing like, is that like an argument that's getting passed to?
Yeah,
Go, or
so
is
n is this group, right? We're going to calculate the products from 2 all the way to 12, right? So whatever the value of n is at this particular time, we're going to increment the wait group counter, right? We're going to say, we're going to start a new set of work, a new chunk of work, and we're going to say, let's spawn this function down here. I'm going to pass it this argument n, which is an integer, right? And down here it says expect x, which is an integer, right? Does that make sense?
Yeah. Okay. So.
Let me scroll this up.
Let's say you had a times table 2 function, and you wanted to add times table and times table 2.
Okay.
Would you say go times table and then go times table 2?
It depends on
Say
it depends
times table 2.
it depends on kind of like what semantics that you wanted to have, I think.
Okay.
Does that make sense?
Yeah. Like.
Go just literally creates a separate Go routine. When you use the term process in Erlang, similar concept. It fires off a process. It's not a thread. They call it a Go routine. They have their own little fancy name for it, but it's a process for all intents and purposes that simply executes concurrently.
It executes this chunk of code concurrently.
And that's it.
For every time I call Go, right, in this loop, it's going to spawn a new process to execute that chunk of code with that argument.
I'm just wondering, what can you pass more than one argument to Go?
Absolutely.
Yes.
You can.
Absolutely.
Hang on, to Go,
Well, to the Go
You
routine.
copy line 14.
you can only pass one function to Go.
You can, okay, that then answers my question. You
Yeah,
can only
yeah.
pass one function to Go.
Yes.
So of course, yeah.
Right,
There's one.
Yes, Go has first-class functions. You can pass functions as an argument to a function.
Okay. And then inherits whatever scope it's got. Like in this case, this for loop as n is increasing.
Mm-hmm.
It inherits it.
There's
Yep.
closures.
Yeah.
Go supports closures, first-class function. Yeah, question.
How exactly is the Go times table tied to the wait group?
Yeah, that's my question. The WG done is really curious there in the I get they're all accessing the same
Oh, I see.
outer scope
Okay.
variable there,
Yeah.
but
Yeah, so this is like a global like a global semaphore.
Which one? It's just literally decrement. Think
okay,
of it
so
as
it's just
one
decrement,
plus
it's
one.
reference counting. So
Yeah,
just really just copy
That's
reference by
that's
reference.
exactly
So
what
there's no reference to anything specific other than
Gotcha.
number.
it's totally a semaphore.
Yep.
It's a global semaphore. It gets incremented globally, gets decremented globally. When it goes to 0, Yeah.
So specifically the answer to my question is line 24 is how it's tied.
Yeah, line 24 is how this and this are connected together. What this says is until this is 0, block. So just wait until that's 0, and then when it's 0, exit. That's really what this encapsulates.
Okay, thank you.
So wait group is one of the many types of synchronization primitives they have.
Go has a lot of different synchronization primitives. Wait group is a really easy one to understand, but they also have mutexes, like specific mutexes. They have a read mutex, they have a write mutex, they have a read-write mutex. They have a whole bunch of different synchronization primitives, and those are all required in many cases because a lot of things are not concurrent safe. For example, updating maps is an activity in Go which is not safe to do concurrently. So when you update a map, you have to set a mutex, you have to write the new value into the map, and then release the mutex so that the map's available for other people to look at.
My question then is, now I'm sure there's an answer, so this isn't a troll.
Go ahead, Paul, troll me.
How is that significantly different than, say, writing a C++ program except for maybe the runtime has certain bottlenecks, like Linux only lets you do 2 million simultaneous threads or something like that, you know, as opposed to 4 million, which would go by the computer. So besides performance elements like
Channels. There's your answer.
Well,
There's channels.
I think there's two answers to that question. One is channels, which I didn't get into here because I thought that I didn't want to introduce that complexity right now. I actually don't have a code example with channels right now. I can add one later, but I don't have one right now because I just wanted this to be like a really simple, straightforward. Here's like the most elementary concurrency problem. But what I was going to say is that for me personally, there was two reasons why I found Go attractive for concurrencies. One is that a lot of the scaffolding that you need to have for mutexes and for semaphores and for all that's provided. Like you get it out of the box. You don't have to write it yourself. You don't have to worry about sort of all the quirks that come along with dealing with operating system calls and all that sort of stuff. And the second reason is that to me personally, this just made more sense. Like I could just reason about it a lot more easily than when I looked at a chunk of C code or C++ code. It just feels more compact to me. And I'm lazy. And yeah, so style, I don't know. It appeals to my aesthetics.
But channels are different, right? That is something actually. So that's interesting.
Well, I talked about channels earlier. Channels are a way for Go routines to basically send events back and forth to one another that have a type. So channels have types, and they can send type messages. And then on the other side of those channels, you can have select blocks that essentially pull things off the channel and then evaluate them.
So the channel is the message in the channel. Is it message the right word?
I think of it more as an event.
Is the event in the channel immutable or safe somehow from being?
It has all of the sort of flaws, if you will, that shared memory systems have.
So you can
There's no specific guarantee from Go necessarily that whatever channel, that whatever message you sent won't be modified somewhere down the pipe.
okay. Without using a monitor or a lock or something.
Right.
Now, that being said, though, reading from the channel
Is atomic.
it is atomic.
Yes.
Right? A read will occur, and then something, even if another Go
Yes.
pays attention to read,
Correct.
it's going to wait until that other read is done, and then it will do the next read. So
the
there is
channel
some level
access-
of guarantee.
Yeah, there is an atomicity guarantee in the sense that once you send a message on a channel, whatever the destination is going to pull them off one at a time, right? So it's going to serialize it for you automatically, and then it's going to be able to deal with it in serial process, right?
Channel access is atomic.
Yes, so reading and pushing messages onto a channel are all atomic operations.
It is very much. It's very much a kind of like a pub sub, and what you'll see in a common paradigm is even with like weight groups or channels, you'll pass references to these channels or these weight groups around to your various functions, so that if you do have 6 Go routines that need to read from this channel that's interested in that data, they can all just pull these reads, and you have a guarantee that it is atomic. You are going to get the data in the order you asked for. That's kind of the paradigm you're going to see in Go.
Right. So actually, one of the things that's neat about Go that's a little bit different from Erlang, just as an aside, is because you can pass a channel as a variable to a function, you can actually read the same data off the channel across different Go routines, right? And in Erlang, you'd have to send that message repeatedly across multiple PIDs to do the same thing.
What's a PID?
A PID is a process identifier. But Jeffrey doesn't know. Yeah, question.
If you removed all of those weight groups, would the main thread just execute and just exit immediately? And
Yep.
you wouldn't, if you replace that weight with like a sleep call, would you actually get some output before it?
No.
No?
No. Because one of the things that a weight group signals to the runtime is that I care about this computation. If you don't have that weight group in there, you don't have a way to signal that you care about this by passing channels or signals through channels, then the Go compiler is just going to say, well, they sent this Go routine, but they don't actually care about the results because they never wait for it and they don't actually send any messages back. So I'm just going to, so I'm just going to not execute it, right? And then it's just not going to do it. And as I said, that was surprising to me, and it was unpleasantly surprising.
A supervisor. Somebody who's saying, hey,
yeah.
let me hang tight until this is done.
Yeah, so that's really what this weight group signals is. I care about this computation. Please execute it for me. And when you're done, make sure you decrement the semaphore. And when it's all done, then execute from your main execution.
Is there distributed programming? You said channels across
Yeah.
systems too?
Absolutely.
Channels and messages
I mean, not out of the box, but there are definitely Go libraries that let you send channel-like messages across TCP connections to other Go runtimes. And there's also Go RPC, and there's a whole bunch of serialization like GOB. There's this whole GOB library that's like the Go serialization, one of the Go serialization libraries. What's that?
It's Arrested Development joke. Never mind, you don't get it. Too dated.
I love Arrested Development, but yeah, sorry, I missed that one. Yeah, question.
So if the semaphore is acting in a way of just like dumping and decrementing, is there ever a point where you can decrement the counter to 0 while you're still trying to spin up processes and have it conclude?
Yes.
Okay.
You definitely could have that condition happen.
Okay.
Yeah,
Absolutely.
It's all done twice by accident. It's a little bit messy, but I've done this.
Okay.
Yeah, so absolutely, you can definitely have that problem, which is to say you'll create a wait group, and then you'll call wait on it, and then you'll say done, and then some other thing you'll say done, and it will decrement it twice, and you didn't expect it, and then it'll have premature.
Right now, I'd see if I have somebody's gonna have an error in format printf, I'm guessing done won't get called because an exception will occur. So if I'm not handling my errors correctly, then I could not release.
Theoretically, yes.
Well, I imagine that's actually something most newbies do.
Yeah, I mean,
newbies don't handle
it-
errors.
yeah. So this is newbie code. Don't copy me. Yeah, question.
I said newbies. I heard you say
In the
that.
practical sense, do you have to worry about among the various platforms whether all the platforms are going to support what you're doing with concurrency?
In the sense of Go or Erlang, or
With Go?
I mean, as far as I'm aware, someone correct me if I'm wrong, but as far as I'm aware, all the platforms that Go's been ported to support all of the basic language specifications.
So you just don't have to worry about it.
Basically, if you get it to compile, it should run on Windows, it should run on OS 10, it should run on Linux, and it should run on anything else that they port it to. Like I heard somewhere that IBM was porting it to mainframes or some crazy thing. So yeah, so if you want to run it on Z series hardware, yeah, exactly.
Does Go, this is like
Yeah.
this is not like a question about Go cover tools, but does Go have like literal data for
Yeah.
vectors and maps?
Yeah, they have all sorts of different data types, tons of different data types.
But a literal data, I know, but like literal representations where you can just
Mhm.
yeah.
Yeah, definitely. They have inline literals. They have literals for all of their data types. Interfaces, channels, maps, strings, runes, integers, all the different integer sizes. They have like 3 different ones. Yeah, they have floating.
So it's a better C.
I think that's a decent way to put it. I would put it as kind of like it's like a system language that's a little bit higher up than C. Like it takes away a lot of the memory management and stuff that you have to worry about there. And a lot of the constructs for building semaphores and building mutexes and blah, blah, blah are all handled for you. And it's all cross-platform, which is another lovely thing. And it's also a single binary, which is another lovely thing about Go, right? So once you get it compiled, then it's what?
Yeah, you can write a lot of REST APIs because that was originally its use case.
Everyone,
System programming languages,
but-
you can rip out like old microservices.
yeah, everyone loves REST APIs,
So
right?
is that pointers?
Yes. They're not C pointers, they're safe pointers.
There's no pointer arithmetic though.
There's no pointer arithmetic, and also the things that you can point to are usually not direct memory access type things. They're usually just like references in scare quotes, to some data type, right?
So you could use me like path by reference type thing, not like
Absolutely.
Okay.
And you can also send a pointer to modify a data structure inside of a Go routine or inside of any random function that you want to create. So yes, it does have that C semantic where you can pass in a pointer to a piece of memory and then modify
But
it.
you couldn't write a draw structure.
I don't know, maybe you could.
Well, I'm just saying like, you know, I guess it's about.
I wouldn't say no, but I personally probably wouldn't. But
How would you write a memory map? You know?
I don't know. But I mean, Go supports unsafe, so if you want to do things that like write device drivers with it, then you could theoretically do that. And they also have a C foreign function interface, which I don't need to get into, but is also there and available. All right, so that's kind of the Go stuff. I've also implemented the same thing in Erlang, 3 different ways, because I love you all. The reason I implemented it in 3 different ways is because I thought it would be interesting to talk about the different ways that Erlang can support execution patterns So over here I have 3 different implementations. I have times table, which is actually an E script. And then I have timestable.url, which is a module version. And then I have timestable2, which I will show you in a few minutes. But first,
It's a mystery.
it is. The reason I have timestable2 is because timestable has an error that I'm going to talk about. And if any of you feel like solving a mystery, you can tell me what the error is.
There's percentage signs everywhere.
Yeah, so Erlang's a really ugly language, people think. I like it. I like Erlang's syntax. I find it quite lovely. But people think that it's ugly. That's okay. If you're a hater, that's fine. I won't judge you. It's okay. Not everyone likes every programming language, and I've just made peace with that. I used to care a lot more about these things, but I don't anymore. So if you don't like this, if you think it's ugly, that's fine.
What's your periods?
Huh?
What's with the periods?
Well, see, Erlang really cares about grammar a lot. It really cares about grammar. And so when you finish your function, you have to tell it you're done, and the way you do that is by putting a period at the end of it.
Why is it okay to get a semicolon?
Because it's a clause, and I'm not done with my function. You'll see here I have compute times, and it has 2 arguments, and down here I have a period.
You're going to have to explain to them the difference between a declarative function with a type and an imperative.
No, I don't have to do that. Look it up. There is a bug in this code. No, and there's not a bug in this code. There's not a bug in this code. There's a bug in the eScript version. We'll get to that in a second. Okay? All right, so this is a very straightforward implementation and it's straightforward to me as an Erlang programmer, of the Go code that I just showed you. The thing that you'll notice the most probably is that recursion is the only construct for looping. And that's the reason I have all these extra functions here. So for example, let's just start top to bottom. I have this function called timestable. It takes a single argument, that's n. As you see, Erlang does not have types. It doesn't say that this is an integer, but it is. And then it calls this thing, compute times n with 12. That calls this function head, which has x and I. And what this does is it outputs a string. This is string formatting in Erlang terms. So it says x and I and x times I. And then we call ourselves again, x I minus 1, until we get to 0, and then we return OK, which means our loop is finished. Let's move down to main. So main has a single function call. It says spawn workers 12.
Workers.
Yeah, so I know this is bottom screen, sorry. We have spawn workers 0, and then we have spawn workers n. And then we have this keyword, spawn, and then we take an anonymous function. The anonymous function says times table n, end, and then we call ourselves again n minus 1. When we get to 0, we stop. Okay?
So you have to write one function to do stuff, and then another function set to have workers do that function.
Well, I could have implemented this in a different way so that there were less function heads, but I felt like as people that were probably new to, how many of you have used Erlang before? Okay, well that's more than I expected. But in general speaking, it's easier to reason about concurrency when you have functions that sort of hide the concurrency and you just call the thing that actually does the concurrency. At least that's been my experience. So what I decided to do was actually have some extra functions that help you see where the concurrent parts are, or sorry, not the concurrent parts, but the recursive parts. Getting my terminology all messed up. So yeah, so basically I would just want to isolate the recursive calls from the actual function calls, so that would be clear that this is recursive.
There's also hoisting, like looks like here.
Yeah, definitely. Yeah, the Erlang compiler is not super intelligent, but it's pretty smart. And yeah, it knows if you actually, it doesn't even care. It will just blindly assume that eventually there will be a function call, and if there is in fact not a function that is called that thing, then it will raise a runtime exception called undef, which I'm sure you're familiar with. So yeah, if you try to execute a function that does not exist or is not exported for Erlang, it will return an error code called undef.
What if we define twice?
Then it.
Second definition works, right? Or first definition.
Or is it immutable?
I don't know. I don't know what will happen.
It's immutable, right?
Yeah. Do you know Jared?
Oh, actually, I don't.
Oh,
But,
okay.
Can we
I
try
was
that?
asking about the
Right
code
now.
instead of.
Oh, you actually have a question about this? Okay. Yeah, go ahead.
Okay.
Why not? I mean,
I'll let him go.
no. What is your question, please?
So my question is, in the Go example, the secret sauce effectively was the Go
Weight group.
weight group
Yep.
combination.
Yeah.
So this would be the, and it's at the bottom of the screen, I can barely see it, but spawn?
Yeah, so spawn workers is the secret sauce here, right?
Okay.
Sorry, it's at the bottom of the screen. I wish I had a way to make it higher.
Inside spawn workers, there's like spawn, I'm guessing.
Yeah,
that is-
there's a keyword. There's a keyword that Erlang has called spawn. And spawn has many different forms, but the form that I chose to show you here is one that takes an anonymous function, and that's exactly what this is. It's fun with no arguments, and it takes a function head called times table, which is defined up here, right? And then it executes this thing 12 times.
That is almost quite literally the Go equivalent. I mean, spawn, you're calling an anonymous function. You're nearly the same.
It's almost identical. There is a version of spawn that actually will take a module function argument, which would maybe be more explicit, but I just felt like this. Most Erlang programmers are going to use this call as I've written it here.
Very JavaScript.
It is a little JavaScripty, yeah. It has that flavor about it. Yeah, again, yeah, scare quotes. What's that?
No reference.
No reference counting. It's just pure recursive. I'm going to do this 12 times because I said literally you have to do it 12 times, right? And up here it says literally you're going to execute 12 products, right? And you're going to output that 12 times. And when you're done, you just return OK instead of executing this again.
You know that's like a magic number.
What?
You know that's like a magic number.
It's what, 12?
Well, absolutely not.
You could label something. You could say.
Well, actually, in the eScript version of this, I have a macro defined as size, which makes it definable. All right, so I want to demo this.
One question before you
Yeah.
go too far.
Yeah.
So that spawn, so trying to mentally picture the Erlang supervisor hierarchy that you were talking about.
Yeah.
That spawn is creating a new actor. How does it know which actor is the supervisor?
Well, there's no supervisor in this particular example at all. There's a group leader, but the group leader in this example will be for the Erlang shell.
Okay.
Okay, so the Erlang shell is the thing is the application we're going to run, and this code is module that we're going to load into its memory. And then when I invoke it, that's the point where processes will be spawned and computations will occur.
Okay.
Now this is a lot more explicit in the eScript version that I'm going to show you in a minute. And you will see exactly where the messages go to and where they come from. So it will be a little more clear. And also originally, there's a really neat visualization technology that Erlang comes out of the box with called Observer. Unfortunately, it requires WX widgets, which I do not have installed on my OS X box. But there is a distribution of Erlang from Erlang Solutions that comes with WX widgets prepackaged, and it does have this program. It's called Observer. And what it does is it shows you a tree view of all of your processes. So it shows you the group leader, it shows you the top level supervisor, it shows you all the workers, it shows you supervisors that have workers. It's quite lovely. There's also another neat thing called Erluby that was written by this Dane called, his name is Creston Thorpson, and he wrote Erjang. Erjang is an implementation of Erlang on JVM. He's a mad scientist.
Yeah, what's wrong with this guy?
Yeah, he's a mad scientist. He's more fun than a barrel of monkeys. Definitely go drinking with him if you have the chance. I highly recommend it. Yeah. So anyway, he has this visualization technology called Erluby. Erluby uses this really neat thing called ubigraph. Ubigraph came out of this company called Ubidity Labs or something like that. Yeah, so they have this really neat visualization technology, and then I guess they went out of business or whatever, so you can't download their runtime anymore, so you can't do visualizations with it anymore. And so I was like, oh, well, I guess I won't have any pretty pictures to show you tonight. So sorry, it'll all be just text, but bear with me. So I'm gonna.
Couldn't you pirate a version of that?
Probably, but I would never do that. FBI would never, ever copyright infringe on anyone. Okay, so times, tables.
Oh wow, there's a just goes into the shell. Period. Everything has happened during the process. Every function has to.
Oh, I typoed it. times table. You know, for pair programming, this is really not going very well.
No, you did it again. Times.
Okay, thanks. Okay.
Okay, times table.
Yeah, so here's my Erlang shell. This is a little shortcut for the Erlang shell. It says compile and load this Erlang module. And it says, okay, I loaded it. Now I can do this. Oh, it didn't. I put 2 colons there. Sorry. I'll just have to type it again. Times. There we go. Hooray! Yeah, so something that you might notice about this that's a little more interesting than the one about the Go one is that the Go output came in blocks, right? I don't know if you noticed that or not, but it came out kind of like, okay, well, you know, the numer, no, that's division. So one side of the product is going to be, you know, this number, right? And then the other side is going to be this constant, right? So whatever it is, it's.
It doesn't matter.
Yeah, I don't know, whatever it is.
Doesn't matter, so there is no 2 words for it.
Yeah, so anyway, we have these 2 numbers, and we're going to calculate the product. And for Erlang, they're kind of more intermixed. You'll notice that they kind of all come at random orders.
Is it just a difference in the schedule? Really?
Probably. That would be my guess. And the other thing that's interesting is that the PIDs may execute variably, across different runs.
Go routines are acting a little more sequentially in there. Not the go routine, the wait group is acting almost sequentially.
There's definitely some sort of synchronization going on under the hood that.
Like execute this batch and then execute this batch.
Yeah, that Erlang doesn't seem to have. So sort of an interesting aside. All right, so I'm gonna get out of that now. Let me reset my screen. So it's at the top here. And then, so let me do this now. Times table. Oh, I should show you the code first. That way you could have a chance of seeing the error. Sorry.
Did you actually just spell tab instead of tabbing?
I did something wrong. I definitely did something wrong. Okay.
All right.
So this is an E script. So E script lets you execute Erlang code basically as kind of like a shell script. Here's a macro. Don't be scared by this. It's completely C-like macro. There's no like Lisp interpretation or redefinition or anything. It's completely text substitution, 100%. Basically, we're just defining size here. So you'll see that these functions are very similar to the other ones. The big difference comes here, where I'm passing around PIDs. So what I'm doing now is I'm giving these functions a way to send messages back to the central PID that's sort of collecting them all and is going to output them for us. And in fact, that is actually the main difference between these pieces of code. Just to walk through it again really quickly, I'm calling times table in with the PID of this thing, the main. And then here we're just executing this size times, right? So we're passing in size, and we're executing this till it's 0. Okay, so that's the same. Let me put this up at the top because it's easier to see. And this is totally different. What this says is for this PID that I got passed here, I'm going to send this message. This message is a tuple that starts with an atom called result, and x and I, x times I, and then self, which is to say what PID is executing this piece of code. And it sends it back to this, the main. So the main is the thing that's spawning all these things. You'll see that it also has self. So that's saying, okay, when you compute this, when you've done this work, I want you to send this message back to me, and then I'm going to do that in this function called listen. And listen is defined down here, and I'll show you that in a second too. Just really quickly, in eScript, there's always has to be a main. Main takes an argument. It's a list. In this case, we're only going to pass it one element, so it's upper bound. That's the number of times to execute this loop. So we're going to convert the integer to we're going to convert the string to an integer. And then we're going to call spawn workers with our self, and spawn workers is still defined at the bottom. It's basically the same. The only difference is the PID. What's wow? Are you overwhelmed?
Yeah. It's just multiplying and it's taking this long.
I know, it's crazy, right? It's crazy.
I should never run early.
This would make an awful lot of sense if you were actually doing something distributed.
Yeah, if this wasn't a times table and was an actual interesting piece of work, then maybe it would be better. But I didn't want to bring in that complexity. So anyway, in listen we have a new keyword that you've never seen before called receive. Does anyone guess what receive does?
It receives messages?
It pulls messages out of the mailbox. That is correct. And it's the only part of Erlang that blocks, or I should, with an asterisk, say the main keyword that blocks in Erlang. So this is the only thing typically that is going to wait for things to come in. And specifically what we're waiting for is this message. So this message, again, is a tuple. It contains X, it contains I, it contains our quote, which should be prod. And then it has from. From is the PID that the message came from. And then it just outputs that. So it does IO format and outputs it. And then after 5,000 milliseconds or 5 seconds, if we don't get any messages like this, it will actually say timeout and then it will halt. So it will stop.
So that message on line 27, is this effectively unrolling or expanding the tuple, or can you omit pieces of the message, or are you expecting the whole message there?
For Erlang purposes, you have to pattern match on the entire thing. But what I could do is assign this to a variable, and then whatever comes in, it will just accept. Right.
Okay.
But see, over here, my IO format actually has 4 arguments. And you'll notice there are 4 arguments here.
And that arrow syntax is kind of like just piping it to the...
It's saying, so...
Is that a
function, right?
No,
is that like a lambda expression? Or
sort of. Really what it means is, if you get a pattern match here, then execute this chunk of code.
Oh, with everything kind of just passed on to it.
Completely, that's exactly what it is.
Not like a unit pipe almost.
So what happens is the values that come in for this message get bound to X temporarily, bound to I temporarily, bound to quote temporarily, and bound to from temporarily. It executes this code block, and then all of that disappears.
Oh, okay, cool. You said all this just out of morbid curiosity. What is the life cycle? You say it disappears immediately after that block it executes?
Yes.
Nice.
Yeah. Actually, it's when this executes, technically.
So there's your scope right there.
Yeah, the scope is from here to here.
Nice. Okay.
It's from receive all the way to end.
Why does halt take an argument of 1?
Because that's the value that I want to output to the shell.
Exit code. Yeah.
It's an exit code to bash.
Right.
Yeah, you can
You have all these different matching patterns.
you can have as many patterns in here as you want. You can have from 1 to n. In this case, we only expect 1 message because that's all we're generating. It's very easy to have. You can also have underscore. So if you can underscore matches anything in Erlang, and if you just want to discard things, you just match underscore, and then you don't execute anything. You just return OK or something. Everything in Erlang is an expression. That means everything has to return a value, even if it doesn't do anything. So in this case, it's returning the value from this function, and in this case, that function returns OK all the time. Always. So I'm not even capturing it. Later, I'm going to capture it. Now, can anyone spot the error in here? Anyone got an idea of what the error is?
I was gonna say you got a really specific pattern match. So
That's a good guess, but that's.
You have like a trap clause, wouldn't you? At the end.
Yeah.
I'm going to make everyone look smart. Is it line 30 where halt 1 doesn't have any syntax at the end?
No, that's fine. That's fine. That's fine. That was a good guess, but that's not it.
Wait, so it's fine to not have a period?
Yes, in that particular case, it's fine.
Is it
Because it's halted?
on this?
That's a case when Erlang does not care about periods.
Okay.
It cares about periods until it doesn't, and that's where it does.
So why should you have it on 36?
It has one there because that's the end of this function. It does not have one here because this is actually the end of my statement.
Yeah, so I got a question.
You'll see there's a comma here, but there doesn't have to be one here.
I see you're recursively line 32 calling, listen again. Yeah, I thought that the main was actually handled that from the messages being passed by the function
Receive is the only thing that drains mailboxes.
No, I understand that, but if you scroll back up
So
to the main,
so if I put one listen without recursion, it's only going to take the first message and exit.
That's it. Huh?
That's it. Because receives exactly one and only one message, and then it's done.
I just thought the recursion was up in the times function.
Yeah.
Calling
Well-
main, but it was passing a message to main, right? That's what your PID was. It comes from main, passes the PID of main to times table.
Correct.
You're calling PID. You're sending a message to PID, which is main.
Yep.
Which calls listen.
Yep.
Every time it's called.
So listen
The
is
recursion was there.
listen is the place where where these messages are being drained. So the messages are being put into the mailbox,
Okay.
and the mailbox is sort of the channel-like construct
Yep.
that serializes messages that come into Erlang.
Did it pass self to listen? Or something like that? Like,
Oh, you mean as far as what the error is?
yeah, I'm trying to figure out
All right, well, let me execute this, and then maybe the error will be more apparent.
Yes, let's see Mark's mistake.
Hey, I don't have to type this one then. Did I type that right? Looks right. Okay, so this time you see what happened here.
It didn't
Oh, there's a lot of
time out.
ones. But
So-
that doesn't matter, right?
There was no exit condition.
That's the problem.
Yeah.
So look what happened at the bottom here.
Find out.
We got our timeout. We don't know when we're done. That's our problem. We don't know when we're done. How do we know when we're done? When is the receive loop supposed to end? Right? In Go, in Go we have this wait group. That's what signals the end of the program. In Erlang we don't have that, right? So we need a way to have that. And that's the problem with this code. So what I did in the second version of this, which I'm going to show you right now, or just in a second. Let me clear this again. I'm going to show you the second version now. Not that one. Two. Okay, so this is identical code. And the difference here is that we're passing listen and argument now. In fact, what we're passing it is the number of responses we've gotten and the maximum that we should expect. And then what we're doing down here is we're pattern matching on that. And remember earlier you asked me how do we maintain state? Well, this maintains state. The reason it maintains state is because down here we compute a new received value every time we get a message. You'll see we get a message in, right? And this time the arrow maybe is better because it's indexed or indented correctly. You'll see that we execute the output, right? And then we increment this counter that says, oh, I got a response, and I'm expecting max responses. So what this says is when R is max, or when they're identical, to be more specific, right? When R and max are the same value, then we just return OK.
With R and R.
Correct.
So it'd be the same number.
Exactly.
It's going to end.
That's right. So when these values are the same, right? When max is the same as R, we're going to execute OK rather than we're going to listen with new R and max.
So how does the R+1 work in a?
This is an expression return, right?
Yep, that's exactly what it
Well,
is.
yeah, but you might have two things happening at the same time.
But only one branch of this code is going to get executed.
Last take two.
Okay, I gotcha.
So there's only going to be one. So even if there were multiple messages here, only one block of that code would be executed, right?
Yeah. So that's going to only execute within one number of that. So like one.
Well,
So
as an example, let's say that we had two different messages that we were expecting, right? One is this result, and the other is, I don't know, foobar, right? So what we would do in the case of matching on foobar is we would just return the same R that we already got, right? So instead of having R+1, we would just return R, right? And then the next time we execute the loop, R would be the same value as it was before. And when we get the new result, then we'll increment it. That's the only time we'll do it. So the big difference here is that in Erlang, mutation of state is always explicit. There's never implicit mutation. You always have to explicitly say, that's what I want to mutate. That's the only thing I want you to change.
There's no such thing as a side effect.
That's not fully true, but it's generally true. Yeah. With air quotes, I will totally support you to say that.
Like that IO format. That IO format's obviously like side effect of the console.
Okay, yes.
But
Yes.
can't-
I probably spoke a little too broad.
For state mutation, it's explicit, and it's always explicit. So in this case, we know when we're done, and so we know when this is supposed to exit and stop listening. And then you'll notice up here, I don't even have an after. There's no after clause here at all because I don't need it, right? The code executes and it stopped. Yeah, I got rid of it because it took up too much space. So let's execute this just to show that it works correctly. Times table 2, 12, and then there's that. And then just for fun, I wanted to do. I think I typoed that. Let me try again. Yeah, I typed times. That's funny. Oh, that was super fast. Yeah, I got it.
That's why it's so fast. Good job.
Yes. It's really hard to do without. I wish all my code ran that fast.
Right.
There.
Pretty quick.
So So you can see Erlang's pretty fast, even when it has to dynamically compile code and execute it. Now, the thing that's unfair about this is that the cache of OS X is already hot with this code, so it's already sitting around memory. The dirty page is already sitting there. So that's an artificial speed increase, but it's still pretty fast. And then I didn't mention this before, but this thing in parentheses over here, this is the actual PID identifier. So if you scroll back up through here, you're going to find that there's 12 unique PID identifiers, and they all have this format, which is angle bracket, and then some number dot 0 usually, and then close angle bracket. And these PIDs are unique per Erlang node, so you can, as I said, location transparent, send messages across distributed Erlang to other nodes remotely. So it's quite nice. Are there any questions about this? Yeah.
So the version for your Erlang is actually coming down versus the Go version is coming up.
No, it's just a race condition.
Oh, you mean in terms of like how the things are being generated?
Just for like the times table, so there's times table going down and
Yeah. So the loop and Go increments, and then one in Erlang decrements, and the reason it does is because of recursion. It's just easier to detect when I hit 0 rather than when I hit 12. I could have written it the other way. I easily could have written it the other way if I wanted, but anyway. So let me yeah.
I just wanted to clarify. You said you can send things from one PID to the other across Erlang hosts. So does that just mean that sending things from one PID to the other, it's kind of doesn't matter if it's across the network or not?
Yeah, that's exactly what it means. I mean, it does get serialized. It does get sent across. Like if you have Wireshark or whatever listening on the network, you will see the traffic go across the wire.
But that's not, that detail is really exposed to.
As a programmer,
I gotcha.
the mechanism for having to worry about that is completely transparent to you, right? The message just magically shows up, and you handle it exactly how I showed you here with a receive clause and the message pattern match, and you execute some chunk of code, whatever that is. So it's quite nice. Let me get back to. Let's see here. Let's see if I can try to do this again. Yes? No? Oh, come on.
Can you do message passing with something that's really large? Some, I mean, large is a relative term. I'll say it's like, I don't know, 100K.
Yeah.
And is the Erlang scheduler smart enough to, if you're passing it from one process to another process, and both those processes are on the same machine, not across the network, is the scheduler smart enough to not do a hard copy of that and pass like a pointer, or does it like have to do like a deep copy? Am I phrasing that correctly?
I'm not sure I understand your question, to be honest.
So I'm thinking about like persistent data structures where like everything is always shared memory, and I'm wondering if you had something, large in Erlang, and you were passing it, message passing from one process to another process.
Yeah.
Does it?
As long as it's local on the same node, and as long as it's binary, then you won't be doing you'll pass a reference to it.
What classifies as binary? Like what if you just had a?
Erlang has a literal binary data type, so that's what.
What's the is it structs? No, records. What if it's a record?
Yeah, records get passed completely.
Hard, like it's
Yeah.
copied.
Yep.
So if you have something that's say a megabyte.
In a record.
Yeah, if you have a megabyte record.
That will make you sad.
Okay. Yeah. Well, because I was looking at this text editor idea, right? I was doing this thing where I was going to store all the state and just have everything. Any possible change you make gets like passes that state around, and it was like this isn't going to work.
Yeah.
As enclosure that would work great because it's all persistent and it's shared in memory, but it wouldn't work.
Yeah. So you.
Explicitly optimized for that scenario?
You'd have to offload it somehow so that it's not being explicitly passed around, right? Like you'd have to store all of the.
Small parts of it.
Well, I was going to say is you would probably store some sort of notion of history in an ETS table or whatever, and then you'd be able to pull things out of that.
So you want to keep your message passing smallish.
As much as you can, right? Right. I don't know what happened to my display.
Maybe because you have a white computer.
Maybe. I don't know. Something happened there. I guess I'm just going to wing this. What's that?
White computer.
don't even know what happened to my cursor.
Anybody?
Yay, resources that are too small for you to read. Yeah, so here's the GitHub repo. I did tweet about it earlier. Again, I'm at biteme.org or biteme.org. That's my Twitter handle. It's just Erlang and Go. My GitHub user ID is mrallen1. And then I will tweet this again. If you follow the Golang Houston Twitter account, I'm sure they'll retweet me, right, Michael? Right?
Definitely.
Okay, so there you go. Just follow that and you'll get it. There's a really cool Go implementation of all of the problems that Tony Hoare put in his CSP paper. It's on GitHub. But it's also available from Godoc. You can just read the documentation if you want to. It's a package called CSP. It's really cool. So go to Godoc, type in CSP, and you will pull it up. There's another great introduction I talked about earlier that compares Erlang and Go concurrency in a little bit different fashion than what I've talked about tonight. It's similar, but a little bit different. It brings up some nice points. This is a really nice, short, 20-minute YouTube introduction to sort of the primitives of Go concurrency. It's from .Europe or .Paris or .Go or something. There's some European Go conference, and Matt Aimonetti was a speaker there, and he talked about concurrency. This was the post that I talked about where the times table problem came up originally. So there's a link to that if you want to read it. I did a talk at Midwest I/O 2 years ago about designing a real-time game engine in Erlang as an excuse to teach people how to program in Erlang. So if you're interested in Erlang concurrency, like with OTP supervision and gen servers and all sorts of other cool stuff, you can watch that talk. It's pretty short. It's about 40 minutes. All the code for that is also on GitHub. It's publicly available. You can read it. I also talked about Dijkstra, Tony Hoare, Carl Hewitt. If you want to hear more about those guys, I did a talk called The Early History of Distributed Systems, which is also a pretty short talk, about 50 minutes, that goes through approximately 21 papers from 1965 through 1978 that talk about all sorts of interesting distributed systems problems. So there's a whole bunch of interesting URLs that you can follow up with. Yeah?
So I guess the thing that wasn't really addressed that's a big distinction between the two other than weighting or pattern matching is on Erlang you can do this in a distributed way. And this might be a naive question, but is there much approaches for distribution with Go?
Out of the box, I don't think so, but I know that there are definitely tool sets that let you do distributed message passing in a more location transparent manner than kind of what you get out of the box.
primitives are all there in Go.
They definitely are.
Nothing that baked in.
Yeah, so I know one of the Docker projects was this thing called I think it was called like lib network or something like that, and its whole purpose was to do distributed Golang channel style messages across Go runtime instances. Yeah, Ryan.
So Erlang's really old.
Yes, it is.
No, but I mean it's remarkable, like how it has literally been around so long that now the concepts are really applicable now.
Yeah, it turns out that telecom scale is like what you want for internet scale too. So
yeah, which now makes sense in retrospect. But I guess I was going to get at was so it does multi-core like out of the box really great. Was that something that was there originally, or was that something that developed later on?
The SMP support came out of Ericsson probably with about 15 years ago.
Oh, okay.
So around 2000-ish, that's kind of when it got put in. So it may be a little bit later than that. It's between 2000 and 2005. I can't pinpoint the exact date, but it's in that time frame. So Ericsson developed Erlang originally to run telecom switches, and it still does. Actually, your mobile phone probably talking to Erlang right now. It got SMP support added to it by Ericsson. Ericsson still supports Erlang, still is the sort of project maintainer or whatever. But Erlang has been around for a super long time, since 1996, I think, something like that.
Distributed stuff, I think, might be longer. I thought it was the 80s. I could have sworn it was when it started.
86, I think, is when they first like prototyped it with Prolog and so.
Well, I like being a language. I'm not like you, but I'm a minor person. But the message passing and the remote stuff, was that originally part of it?
As far as I know, yes.
Okay, so that's like a fundamental concept.
Yeah, the distributed. EPMD has been part of Erlang for a super long time.
Okay.
So, yeah. Question in the back.
So I know you started out saying that the Erlang syntax was a little off-putting. It's not.
It
language, so
yeah.
This is more of a side, but have you looked at Elixir on top of it?
I have, and if you think Erlang syntax is ugly, then I would encourage you to look at Elixir. It's Ruby-ish, although it has almost no Ruby semantics. So don't go into it thinking that it will behave like Ruby. Another thing that is very interesting to me from a semantic perspective is Pony. There's a new programming language called Pony. It's really, really cool. It has a ton of Erlang semantics, but it actually is faster and safer in the sense that it shares some of the same sort of runtime guarantees for garbage collection that actually improve on garbage collection in Java and in Erlang both. So yeah, Ryan, you have another question?
Is that a Pony? Is that like on its own runtime, or is that hosted on another?
Yeah, it's completely an independent thing. The compiler is called PonyC. So if you wanna check it out on Google, that's what you should search for, PonyC, or Pony language will also, Ponylang will get you.
How long has that been around?
A couple years. It's really it's super new. Yeah, super new. It's really neat. It's really, really interesting. Shares a ton of concurrency semantics with Erlang.
Have you ever used Lisp flavored Erlang or LFE?
Yeah, LFE. If you like Lisp and you like Erlang, you'll love LFE. So.
Do people actually use it, or is it just like a
Yeah, absolutely. People definitely use it. We're looking at using it in Basho actually for some of our stuff. Yeah, as an embeddable programming language.
You could use PAR infer with LFE.
All right, Chris is all plugging PAR infer. So if you do parentheses, check out PAR infer. Hi internet stream. All right, any other questions? Cool. Thank you very much for your attention. I really appreciate your time. Thank you for bearing with me. Thank you. Appreciate it.